Hello, my name is Roy Simpson. I'm a professor of mathematics at Cosumnes River College in Sacramento, California. This is part C of a lecture on, basically a review on multiplying and factoring polynomials. This specifically, we're going to focus on polynomials and factoring polynomials. Uh, I'm only going to talk about a strategy for factoring. I'll review some of the factoring methods and whatnot, but this is definitely not meant to be me teaching somebody how to factor, except for one thing. I will show you I'll show you how to factor a trinomial where the lead coefficient is not 1. So we'll go ahead and start by listing out a method to factor polynomials. The first step, whenever you're asked to factor anything, is to look through what you're given and see if those terms share something in common. Whatever they share in common is called the greatest common factor. So you want to definitely factor that out. This includes factoring a -1 off the highest powered monomial term, which from now on I'll call the lead term. The lead term, it really is a definition in mathematics where the lead term of a polynomial is the term that has the highest power. So if it's negative, I would factor that off as well, just because it makes your life a little bit easier if you do that. Now, if you have two terms, so after you're done factoring out the GCF, if there are two terms in your polynomial, so it's a binomial, then there's one of three things it could be. Either it's a difference of squares, or it's a sum, or it's a difference of cubes. Now, just to let you know, the difference of squares I'll work on in this video. Sum and difference of cubes actually is generally taught later on. Do not ask me why. It's not something that I would choose, but I think for now we're just going to focus on seeing difference of squares. Sum and difference of cubes are for a different lecture, so we're going to put this on hold. Okay. And then the next possibility, well, if you have three terms. In this case, you have what's called a trinomial. There's two distinct possibilities here. You either have a trinomial of the form x squared plus bx plus c, which in this case I just call this simple guess and check, which means that you're just guessing and checking at the factorization. We'll talk about that in a moment. And then you have the more complex one where the coefficient on x squared is not 1. Instead, it's something else. So you have an ax squared plus bx plus c. And there's a lot of different methods. In order of what I think is the best way to tackle these, I would start with a guess and check. In other words, I would go ahead and try to factor that trinomial just by guessing at the factorization. If I spend more than 30 seconds on it, or even 20 seconds on it, I switch gears and I go to a method that is commonly called the box method, or I've heard it called the diamond method. I used to teach it as the AC method. They're all the same thing. But to be very honest with you, I'm going to teach you something in this lecture that is the same thing as these methods, but it's a little bit easier to understand actually. So we'll call this I don't know. It's not really my method. I found it out from one of my students in a previous semester who learned it from their teacher, but I'd never seen this before. So I'll call this best method. Beyond the guess and check, by the way. The guess and check really is the best method. And then the last possibility, at least at this level, okay, because honestly, some people will look at this and say, well, wait a second. If there's three terms, it doesn't have to be x squared plus bx plus c. It could be x cubed plus bx squared plus cx or something like that. Or it could be x to the fourth plus bx squared plus c or something different. At this level, we're going to deal with these kinds of polynomials. But there still is a possibility if there are more than three terms. So I'll say if there are four or more terms. If that's the case, then your only hope is factor by grouping. which a lot of students, it's like a feast or famine on that. I have some students that love it. I have some students that absolutely hate it. So, but you can always use factoring by grouping actually for a lot of your problems. Then we'll go ahead and start through a series of examples that hopefully will illustrate this idea that I've just mentioned. So let's try to factor 4x squared z plus 8x z. First thing you should do whenever you approach a factoring problem is you should ask yourself, do these two terms have something in common? Well, I know that they both are divisible by 4, so I'm going to at least pull out a 4. And then you look through and you see they both have an x and a z. So I'm going to write x and z. Now, the rule of thumb here, and maybe I'll even write it on my method back here, the rule of thumb is to factor out the lowest powered occurrence of each variable. And in fact, those variables that you factor out, they should be common variables. In other words, every term should have them. So you should factor out the lowest powered occurrence of each common variable. And so I see they both have a common variable of x and z. The lowest power of x between the two is just x to the first. And the lowest power of z between the two is just z to the first. So that's how I decide what to factor out. Now, it may seem complicated for people who've been factoring for quite some time, but this is so that you get prepared for more advanced factoring techniques. To know what goes in these little spots right here, and there should be a plus separating them because there's a plus separating these two terms, you have to realize that factorization is the opposite of distribution. In other words, distribution is just multiplying that 4xz back through these parentheses. So therefore, factoring must be dividing 4xz out. So you had in this position a 4x squared z, and you're dividing out a 4xz. And when you do that division, you see the z over z becomes 1, 4 over 4 becomes 1, and x goes into x squared one time. So when I finish that factorization there, I see that I end up with x. The original term that was in the second spot was 8xz, and I again am factoring out or dividing out 4xz. Z over z just turns into 1, x over x turns into 1, and 4 happens to go into 8 twice. So that's what goes there too. And if you look at this statement now, this is a much cleaner statement. Something else that I should probably mention now that I'm kind of thinking about it, because I usually write these things just off the top of my head as I'm kind of going along. I don't really plan out any type of a video lecture here. There is a fifth step, and that's rinse and repeat. That rinse and repeat step is very important because essentially after you're done factoring using one of these methods, you should look at your answer and go, can I factor that any further? You should always ask yourself, can I factor any further? The ultimate goal actually with factoring is to get down to the fewest number of terms as possible. Here we started with 2 terms, 1 and 2. And notice in our answer, it is 4 times x times z times this picture. In other words, it's just a bunch of things being multiplied here. That is a single term. We went from 2 terms down to a single term, and that's exactly what you want to do with factoring. All right, so let's try another one here. By the way, if you look at that previous answer, nothing really can factor out from this anymore, so we're pretty much done on that one. Let's try something else. Let's try the following. How about 15 r squared s plus 18r s squared? Let's see, minus 3r. Let's try that. Now, first of all, I notice that this has 3 terms, so I know this is going to be a different. If it does factor in a special way, I'm going to do some type of trinomials factorization. But I still ask myself, do each of these terms have something in common? And they do. I see 15, 18, and 3 are all divisible by 3, so I'm going to factor a 3 out front. I also see that the common variable they all have is an r. and the lowest powered occurrence amongst them is just r to the first, right? There's an r to the first here, an r to the first here, and an r to the second. I wouldn't factor out an r to the second because these last two terms don't have enough power to lend to pull two powers out. Once I'm done factoring out 3 times r, I will then ask myself, well, okay, in this first position here, there was a 15 r squared s. By the way, I'm not going to go this slowly for very much longer. That's what was there. We are dividing out or factoring out a 3r. So I see 3 goes into 15 5 times. R goes into r squared r times, and the s is still there. Plus, in that spot, there was an 18 rs squared, and I'm again factoring out a 3r. 3 goes into 18 6 times. The r's will cancel nicely, and this is just an s squared. Finally, I have this minus, and then it was a 3r, but I'm factoring out, well, 3r. So that'll just be a 1. So my final answer is 3r. If I want to write it in descending power order, you usually write the highest degree monomial term first. Well, you see there's two terms here with that are actually of degree 2. This 5rs is degree 2 because r lends 1 power, s lends 1 power. And the 6s squared is also degree 2. So it doesn't really matter which way you write this. Some people would prefer to write it as 6s squared plus 5rs minus 1. But it really doesn't matter. And this does not factor down at all. You can kind of see if it does. This is where that guess and check method comes into play. If I look at this and I say, well, okay, I want to see if this factors down, you're looking to factor it down to two binomials where the lead terms in each binomial have an s, because this can be s times s will give me the s squared. And it's either going to be a 2 times a 3, or it'll be a 6 times a 1. But in either case, you're going to have an issue. The only way you can get a constant through multiplication is if this is a 1 and this is a 1, right? 1 times 1, that'll give me 1. Of course, one of them has to be positive or negative. Same thing here. If you do this multiplication out, distribute, notice I don't have the signs in there. It doesn't matter. I don't have any r's to give. If I force this to be an r, well then 1 times 1r would give me an r in this spot right here. So the issue here is that there's not enough variables here in this trinomial to allow for factoring. So I'm just going to not even bother factoring that. There's no possible way. By the way, some people might say, well, wait, I can get it to factor because it was 6s. Here's a 1. Here's an s. Here's a 1. And if I have this as a positive 1 and this is a negative 1, when you multiply this out, you get 6s squared, which is true. You get a positive 6s minus s, right? That's from positive 6s there and then a minus s there. And then the minus 1. But if you notice when you add this up, while the coefficients are fine, it's exactly what you want, you're missing a variable, aren't you? There's no r here, and there's no way to get an r in there. So while you do have a 6 and a 5 and a negative 1, you're missing the r, and there's no way to sneak it in there with the factorization. So this is the answer right here. There's no other factorization of it. So let's try something a little more advanced here. 4 times the quantity x minus 2 squared minus 8x times the quantity x minus 2 cubed. Now these two terms have something in common, at least one thing in common. You see they both share the fact that they're divisible by 4. But they also share another picture in common. They both have this picture x minus 2 here. So I'm going to pull out an x minus 2. And remember the rule, if they share a variable or a picture in common, you pull out the lowest powered occurrence of that. Well, this is a power 3. This here is a power 2. So I'm going to pull out a power 2 version of that. Since this first term does not have a single little x hanging out, I cannot factor x out of it. So let's see what happens after we factor the 4 times x minus 2 quantity squared. Well, in the first spot, it was a 4 times x minus 2 quantity squared. And we're dividing out the 4 times x minus 2 quantity squared. That's just going to be a 1. Minus. In the second spot, we had 8x times x minus 2 quantity cubed. However, we're pulling off 4 times x minus 2 squared. 4 goes into 8 twice. That x has nothing to cancel it. And then this picture is squared on the bottom and cubed on the top. So when you use the power rule for exponents, you know if you have 3 objects of the same objects on top and 2 of those objects on bottom, they'll cancel out and you'll have just 1 left over on top. Now this is not done. When I see something like this, I immediately think, oh, I hate parentheses in parentheses, so I'm going to clean this up quite a bit here. Let's go ahead and do that. So this is 4 times the quantity x minus 2 squared. Leave that alone because you did a lot of work to get to that point. And this is just 1 minus, let's see, a negative 2x times x is a negative 2x squared. A negative 2x times a negative 2 is a positive 4x. And now let me rewrite that in descending power order because it's not so obvious to me whether it factors or not. So I get this, a negative 2x squared plus 4x plus 1. Honestly, I really hate negatives as my lead coefficients. And if you look here, this lead coefficient inside this parenthesis has a negative on it. So I'm going to go ahead and factor a negative out front. And when you do that, all the signs inside this trinomial swap. So it becomes 2x squared minus 4x minus 1. Now you can start seeing if this will factor nicely. It won't, but let's go ahead and just pretend as though we didn't know that. We'll just try some combinations with the guess and check method. If a trinomial factors, it's going to factor into the product of 2 binomials. I need 2x squared, so this lead I'll call 2x and this one x, so when I multiply them together I get my 2x squared. And then the last terms in each binomial have to multiply together to equal a negative 1. The only choices really are a 1 and a 1, and one of them has to be negative. Well, it doesn't matter which one you choose to be negative. If you look at this, 2x times 1 would be a 2x, and 1 times x would be an x. There's no way to combine these with plus or minus signs to get to a negative 4x. There's no way. You can't, there's just nothing you can do to combine those two. So there's no way to get this to work out. So this does not factor. It's prime at that point. By the way, we call that a prime polynomial. That trinomial is prime. Just like a prime number, you can't factor any further. Now let's start getting into trinomials that do factor. First I ask, do all 3 of these terms share something in common? The answer is no. Second thing I'm going to do is rewrite this in descending power order. So it's x squared minus x minus 6. If this factors, that's a big if, but if it does, it'll factor to the product of 2 binomials, and I need their lead terms to multiply to x squared. So that would be an x times an x. That'll give me an x squared. I'll need the back terms to multiply to a negative 6. Here are my choices. 1 and 6 or 2 and 3. Really, there's no other choices. No other 2 numbers, or maybe I should say no other 2 natural numbers multiply to become 6. So those are my choices. Notice that I wrote them down below. Then what I generally do is I ask, okay, well, if I'm going to use distribution to try to get back to this trinomial, I already know 1 times 6 is going to give me that 6. One of them will have to be negative though, but I'll take care of that in a moment. And the same thing with 2 times 3, that's 6, and one of them will have to be negative. So I start asking myself, x times 6 and an x times 1. That's a 6x and a 1x. Is there any way, with positives or negatives in front of these numbers, is there any way to add them up to become a negative 1x? And the answer is no. There's no possible way. If this is negative 6x and I added or subtracted 1x from it, I would only get to negative 5 or negative 7. Same thing if it's positive 6x and I added or subtracted 1 from it, it'd either get to 7 or to 5. So there's no way. This is not a good candidate. So let's see if the second one is an option. Let's see, when I multiply x times 3, I'll get a 3x. When I multiply this x times that 2, or that 2 times that x, however you want to call it, I get a 2x. And there is a way to combine these two so that they become a negative 1x. It would be if the 3 has a negative and the 2 has a positive. That would be a negative 1x. So the 2 will get a positive and the 3 will get a negative. Check your work. X times x is x squared. A negative 3x plus another 2x will give me a negative 1x. And finally, positive 2 times a negative 3 is negative 6. That is the guess and check method. Very powerful, very fast method. I recommend that you spend some time getting to know it. There's a lot of little things that I'd like you to self-discover about this if you were really bad at it before. But for the most part, it is just literally guessing and checking. A couple good hints. As a rule of thumb, if you're working through a textbook homework problem, generally they don't factor as 1 and 6. Okay, they usually factor as these oddball ones in the center. So just kind of keeping you on your toes about that, letting you know that often you can go for the throat and not do the 1 and 6 factoring. Let's try another one here. I have a 7x plus 4x squared minus 2. Now, I know that all three of those terms do not have something in common, so I'm not going to bother factoring anything out. I'll rewrite it, though, as 4x squared plus 7x minus 2. And again, I'm going to just try to guess and check my way around this here. Hopefully, it factors into two numbers where the lead coefficients multiply to 4 and the last terms in each of these binomials multiply to 2. Let's see, two numbers that multiply to 2 are just 2 and 1. There's no other possibility. And now for the lead coefficients here, it could be a 2x and a 2x, or it could be a 4x and a 1x. So notice now you have choices. So I'm going to put the 2 and the 1 here, and then I'm going to create another, oops, I didn't mean to erase all of that. I'm going to put another binomial set over here and say this is 4x and this is, it should have been 2 and a 2, sorry about that, 2 and a 2. And the other binomial set will have the 4 and the 1. 2x times 2x is 4x squared, 4x times x is 4x squared, so both of those start fine. There's only two ways, or one way to get the number 2. It's 2 times 1. Well, technically it's 2 times 1 or 1 times 2. But honestly, in this first case, ordering does not matter. And if you check this out, 2x times 1 is 2x, 2x times 2 is 4x, so I'd have a 2x and a 4x, which would be 6x, and there's no way that I can combine those in any way to get 7x. So this is not a possibility. However, on the other end over here, we have two possibilities. This could be a 2 and a 1 or a 1 and a 2. Let's look at this. 4 times 1 is 4. 2 times 1 is 2. So 4 and 2. Is that any way to combine 4 and 2 to get to 7? No. So that's not a possibility. Then look at this one. 4 times 2 is 8. 1 times 1 is 1. So 8 and 1. And there is a way to get 8 and 1 to become 7. If it was a positive 8 and a minus 1. And double check, is a negative 1 times a positive 2 equal to that third term? It sure is. So this is going to be a minus 1, this is going to be a positive 2. So that's how this factors. This factors to 4x minus 1 times x plus 2. Again, the guess and check. And I don't have to spend that long on it. It really only takes about 10 to 15 seconds before you factor something using the guess and check. But there are some problems that are very difficult to factor. And so I want to show you a method right now to factor a trinomial using kind of like an algorithm in a way, rather than guessing and checking your way around. But I have to tell you before I teach it that the guess and check is always the first step. You should always try that first with factoring a trinomial. But if you just can't get it with the guess and check, then you need some type of algorithm. And what I'm going to teach you is very similar to all the AC diamond method, box method, I forget what they call them now, but there's a ton of different methods. This method is a very cool method, and I hope it helps out. Now, what I'm about to show you is going to look very different from what you've ever been taught. But I want you to kind of pay attention, or really pay attention, to everything I'm going to say here. We started with the polynomial 4x squared plus 7x minus 2. I want you to agree with me, I don't know if you will, but I hope you will, that this polynomial is equal to 4 over 4 times 4x squared plus 7x minus 2. That should be pretty obvious to see that these two things are equal, because 4 over 4 is just 1. So I'm really only saying what's 1 times this polynomial? Oh, it's that original polynomial. So that's the first thing. The second thing that I'm going to hope that you can do here is to take that 4 upstairs and distribute it into the polynomial. If you agree with me already that 4 over 4 is just 1, so that this right-hand side of this equation is equal to the left-hand side, then me distributing that 4 in shouldn't change anything either. Okay, just saying, well, instead of writing it as 4 over 4, I'll distribute the top through and leave that 1 over 4 on the outside. So I have a 16x squared plus a 28x and then a minus 8. And I'm going to factor this trinomial. Even though I'm being asked to factor the trinomial on the left-hand side of the equation, I'm going to go ahead and factor the trinomial on the right-hand side here, because there's something very, very easy about factoring this trinomial as opposed to factoring the first one. Now, of course, the first one's very easy to factor using the guess and check method, but this method I'm teaching you right now is great for factoring if the guess and check is too difficult. In other words, your coefficients might be too large. Your lead coefficient and your constant variables or terms might be highly factorable, which makes it very difficult to do a guess and check method. So let's see, this is 1/4, and I want to split this or factor this into the product of two binomials. I will tell you right now, the choice you're always going to make in this method is 4x here and a 4x there. That is the reason why I chose to say, hey, that original polynomial is like 4 over 4 times the original polynomial. I basically chose that number 4 as being 4 over 4 because that's a coefficient on the lead term, or is what we call in mathematics, it's the lead coefficient. So if I see that lead coefficient being 4, I'm going to say, well, this polynomial is the same thing as 4 over 4 times that. And of course, 4 times 4 gives me 4 squared, or 16, which makes for a very easy factorization. 4x times 4x is 16x. Now, a lot of people will say, but wait a second. That could have factored, we're not done with the factorization at all. That could have factored as 1x times 16x, or as 2x times an 8x, or a 4x times a 4x. It's absolutely true, it could. But I promise you, this method, if you follow this method, it will always factor to be the square root of that number. Okay? Now, the next step is to find out what two numbers that I can park in the back end here that multiply to a negative 8. Well, we have a choice, 1 and 8 or 2 and 4. Right? And one of them has to be negative. Here's the other strength of using this method. In this first factorization up here, if I wanted two numbers that multiplied to a negative 8, I would have said, okay, 2 and 4 or 1 and 8. But with this first factorization, order would matter because these coefficients on x here are not the same. So I'd have to say, well, okay, since I have 2 and 4, I'd have to write 4 and 2. And since I have 1 and 8, I have to write 8 and 1. And then you check all 4 of those instances to see which one is the proper factorization. And if none of those worked, then you'd go to the 2x and the 8x and do 4 factorizations there. And if none of those worked, then you go to the 4x and 4x. Okay, so you see there's a lot of work if your coefficients are highly factorable. But the beauty of having these lead coefficients, the 4 and the 4x, be the same, is that you don't have to worry about ordering. it doesn't matter if I put the 1 in the 8 or the 8 in the 1, because 4x times 8 is 32. 1 times 4 is 4. No matter how I put the 1 to 8, these are still 4s and 4s. Now the second part, so that's two things that are pretty neat. One, that you can easily find your lead term in your binomial factorization. The second thing is that you reduce the number of possibilities in your factorization. And then the third coolest bit is this. If I want the factorization, or basically these two numbers, to be multiplied to become 8, right? Basically a negative 8. I also, and this is what's going to be kind of difficult for you to understand at first, I also want these two numbers such that if I add or subtract one from the other, I can get to this 7. I know some people are going to go, wait, I thought you were trying to get to that 28. No, the power of this method is that I can still stick with the middle term on the original polynomial. So I know that if I had a positive 8 and a negative 1, that would multiply together to become a negative 8, which is right here. And it would add together to become that positive 7x. So here we go. Let's do it. Positive 8 and negative 1. Now you may think, well, this looks like a mess. I'm never going to do this. If you give up now, I promise you that everybody else who follows this method is going to just surpass you. Okay? So this is our factorization at this point. 1/4 4x minus 1 times 4x plus 8. But notice in that last factor here, the binomial factor 4x plus 8, both those numbers are divisible by 4. So I'm going to factor a 4 out of both of these and pull it out front. And I'm left with a 4x minus 1 times an x plus 2. 4 over 4 is just 1, so this is just going to factor into 4x minus 1 times an x plus 2. And at this point, you should be saying, how did he do that? Because that is actually the correct factorization. If you look back at our previous example, oops, that wasn't it. If you look back at this example, 4x minus 1, x plus 2 is what that factored into. And one more. 4x minus 1, x plus 2 is what this factors into. Same polynomial. So the question might be, wow, is that magic? How did that work? I'm not going to tell you yet. What I'm going to do is I'm going to put an addendum to this lecture, a part D, for the proof that this always works. But for now, I just want to do some examples using this method, because I think it's super important to do that. Let's go ahead and try this one. 15x squared minus 4xy minus 4y squared. Again, a guess and check method is usually the best method to do, no matter what. So I'll go ahead and do this using a guess and check first to show you that we can guess our way around to the correct answer. Two numbers that multiply to 15 and add to 4. I'm going to say it might be a 3 and a 5. Those two numbers multiply to 15. Then I'm sorry, I might have misspoke. Two numbers that multiply to 15, and then two numbers that multiply to 4 is what we're looking for. So two numbers that multiply to 4 are 4 and 1, which means I need 4 in the opposite order here, or 2 and 2. And now I'll just check real quickly. I have 3 times 4 is 12. 1 times 5 is 5. So 12 and 5, there's no way to combine those two to get me that middle term, so that's kind of done for. By the way, I'll need y's here. 3 times 1 is 3. 4 times 5 is 20. 3 and 20, there's no way to combine those two, so you're kind of done there. And 3 times 2 is 6. 2 times 5 is 10. Well, 6 and 10 actually can work, right? 6 and 10 can be manipulated to get me that middle term of negative 4, as long as it's a positive 6 and a negative 10. And that's the factorization. And that's what I want to, hands down, make sure that you understand, is that the guess and check method is ultimately a faster method. Now that I've said that, let me reinforce the other method I just taught by showing you, actually maybe I'll do the same chisel point on this one, by showing you how I would do this using the newer method. So I'll write or. Let's see. That polynomial is the same thing as 15 over 15 times 15x squared minus 4xy minus 4y squared. I'll distribute that numerator through. So I'll have 1/15 times 225. Now this is where people balk and they say, no, I'll never do this method. But I'm telling you, you'll miss out if you don't listen. Minus another 60y squared. And as I said, this will always factor to be 15x, so I don't even have to guess what that lead coefficient is. Like up above here, I didn't know if it was going to factor to 1 and 15 or 3 and 5. I guessed 3 and 5. But here, I don't have to worry about guessing or anything. This will always factor like this. Okay? And now I want two numbers that multiply to that negative 60 and add, so let me highlight that. I want two numbers that multiply to a negative 60 but add to become a negative 4. So two numbers that multiply to a negative 60 and add to 4. Well, let's write out some factors of 60 like 1 and 62 and 30, right? 3 and 20, 4 and 15. Any of these numbers, when you try to combine them, 3 and 20, there's no way I can get to 4 that way. So let's see, 5 and 12, we're getting closer. 6 and 10. 6 and 10, those are the winners. So I'll write 6 and I'll write 10. One of them has to be negative, one has to be positive because we're multiplying to become a negative number. I'll choose a negative 10 and a positive 6 because the fact is negative 10 plus 6 will give me a negative 4. And once I'm at this point, I'll just factor both of these binomials. So in other words, the left binomial, the first binomial factor, has each of those terms in there has a 3 in common, so I'll factor that out. I'm left with 5x plus 2. The second binomial, both those terms have a 5 in common, so I'll factor that out. And when I factor out a 5, 5 times 3 is 15. So this will be 15 over 15 times 5x plus 2. Let's see, we factor 5 out of that. That'll be 3x minus 2. And, oh, by the way, y's. There should be y's on these. I forgot to write my y's. Don't forget those last variables. Okay, 15 over 15 is just 1, so this is just 5x plus 2y times 3x minus 2y. Now, often people will say, especially in a classroom environment, because they can't say it now, this seems terribly long. It does seem that way, but it's actually not. It's very quick to do this if you know what you're doing. So let me rewrite that and just show you how quickly I would do this. 15x squared minus 4xy minus 4y squared. I know that this is going to factor to something 15x and a 15x. I already know that. So I write that 1/15. The 15 I would have multiplied through, and I know it factors to 15x and a 15x. The hard part is if you don't look ahead, how do I know what, like these two numbers back here we're supposed to multiply in the previous example, which is this example, we're supposed to multiply to a negative 60. How did I know that? Negative 60 happens to be the product of the lead coefficient, and the last coefficient. If you multiply those two together, that's a negative 60. And a lot of people call that AC. That's the AC method. So I want a couple numbers that multiply to a negative 60 and add to that center term, which is negative 4. Okay, so I know immediately 6 and 10 actually. 6 and 10. And I don't even care about the ordering of it because the fact is, it doesn't matter. Negative 10, positive 6. And I know 3 will factor out of this, 5 will factor out of that. 3 times 5 is 15, so 15 over 15 will cancel. And like I said, 3 factored out of the first one. 5 factored out of the second one. And I'm done. Now, that's me doing it because I know this method. But for those who know the AC method or the diamond method or the box method, this is actually doing the same thing. Notice with the AC method or the diamond method or whatever the heck people call it, you multiply the lead term, the lead coefficient, and the coefficient of the last term together. So a times c is negative 60. Why do I call it a times c? Because it's ax squared plus bx plus c, a times c. And then down here you write b, and b is the middle coefficient, negative 4. And then you write down what two numbers multiply to negative 60 and add to negative 4, and 10 and 6, that'd be a negative, that'd be a positive. And then what people often have done at this point in mathematics is they say, okay, so that means that 15x squared minus 10xy plus 6xy minus 4y squared. If you look at that the central two terms there, negative 10xy plus 6xy is a negative 4xy, so it is actually the same as the original polynomial, but then they factor by grouping. These two have a 5 in common and an x in common, so they pull out a 5x and they're left with a 3x minus 2y. These two have a 2 and a y in common, so a plus 2y, and you're left with a 3x minus 2y. Notice now that you have two terms in your polynomial, and this term, this picture, is the same as that picture, and so you would factor that out front to get the following. 3x minus 2y is factored out front, and you're left with 5x plus 2y. So it is actually the AC method, but it's a faster AC version of the AC method, and it always works. It's beautiful. Let's go ahead and try another one. And again, I will always try the guess and check first. In this case, I see, and again, I always ask what the greatest common factor is. I see that everything here is divisible by 2. So I'll factor out a 2. And I'm left with, what is that? 28? 28 x squared y squared minus xy minus 2. And now I will use a guess and check method to try to factor this. Now there are a couple possibilities of how this factors, because 28 is highly factorable. It could factor to 28 xy times 1 xy, or it could factor to, let's see, the next one is 2xy and a 14 xy, or it could factor to, let's see, a 4 xy and a 7 xy. 3 possibilities. Okay, and I haven't wasted all my time yet. So as far as possibilities, so I'll go ahead and try a few right now. There's only a couple ways to multiply to get 2, either 2 and 1 or 1 and 2. Let's see, 28 times 1 is 28, and then 2 times 1 is 2. So 28 and 2, no way that will ever be a negative 1. And the same thing, 28 times 2 is 56, 1 times 1 is 1, so 56 and 1 cannot be combined to become this middle term. So no possibility there. Second group, 2 times 1 and 2 times 4. That's going to be 2, or 14, I'm sorry. That'll be 2 and 28. No way that'll work. 2 times 2 is 4, 1 times 14 is 14. So we have 4 and 14. No way that's going to combine to become a negative 1. So it's probably this one down here. Let's see, 2 and 1 and 1 and 2. So let's see, 4 and 1 is 4, 2 and 7 is 14, 4 and 14 is, no, there's no way you're going to get to a negative 1, so that's out of the question. 4 and 2 is 8, 1 and 7, there it is, 8 and 7. I want a negative 8 and a positive 7. And there we go. That's the factorization. So this will factor to 4xy plus 1 times 7xy minus 2. That's the guess and check method, just continually going through. It's an exhaustive method, and like I said, when these coefficients here are highly factorable, you're just in for a long haul. Now, going back to the method that I do, which is not a method that people like. I will factor a 2 out of each of these again. So I'm left with a 28. So this first step is always the same, no matter what, just factor out GCF. And then at this point, I'm zooming in on this trinomial. And I'm going to say that's the same thing as 28 over 28 times that trinomial, which I'm not going to rewrite, which is the same thing as 1 over 28 and me multiplying 28 into that trinomial. And I'll let you know that it's just going to be kind of a weird look. I'll say it's a 28 squared x squared y squared minus 28 xy, and then minus, let's see, 28 times 2 is 56. And now I know this is going to factor. Notice I keep that 2 out front the entire time. I know this is factoring to 28xy times 28xy. Two numbers that multiply to this negative 56 and add to a negative 1. Two numbers that multiply to a negative 56 and add to that negative 1. That's 8 and 7, folks. 8 times 7 is 56, and 8 and 1 can be manipulated to be a negative 1. It'd be a negative 8 and a positive 7. I keep misspeaking, but it's a negative 8 and a positive 7. Negative 8 plus 7 is a negative 1. Negative 8 times 7 is a negative 56. And now you just look at these and think, can I factor anything out? For example, in this first binomial, I can factor a 7 out. In the second binomial, I could factor, let's see, a 4 out. So if I factor a 7 out of the first one, I get 4xy plus 1. Factor a 4 out of the second one, I get a 7xy minus 2. That's 28 over 28, so those cancel nicely. And so this is completely factored as 2 times 4xy plus 1 and a 7xy minus 2, which is exactly what we found when we did the guess and check. Keep trying this method. It may seem bulky at first, but again, when I approach this method, I would, so this would be me. If I were to do it, I would again factor the 2 out first. So I'd have that 28x squared y squared. This is full speed, okay? Minus xy minus 2. And I know that's going to factor 2 times 1 over 28 times 28 xy, 28 xy. Two numbers that multiply to a times c, which is 56, and add to a negative 1 is 8 and 7. It has to add to a negative 1, so it's a negative 8 and a positive 7. And then I can factor the 7 and the 4 out. So I'll have 2 times, let's see, factored out 7, so that's 4xy plus 1. And factored out the 4 will be 7xy minus 2. That's full speed. So you see it does happen very quickly. Guess and check takes a lot longer sometimes. Nearing to the end here, I'm just going to go ahead and do maybe one or two of these examples, probably just the one. This is a binomial here. Neither of these terms have anything in common. They're not divisible by 2 or 4 each, or a or b each. But because it's two terms, I know it's a special factor. If it factors, it's a special factorization method, like difference of squares or sum or difference of cubes, which I haven't talked about yet. A difference of squares is, the formula goes like this. You have some first object being squared minus some last object being squared. It will factor to first minus last times first plus last. If you multiply these binomials out on the right hand side, it will actually become f squared minus l squared. I use the letters f and l because it signifies first and last, and if I used x and y or a and b, they get used too often in problems. It gets too confusing. So if I see a binomial and I think it's a difference of squares, I'm first going to write it like something squared minus something else squared. Well, that first object there, that's actually a 2a being squared. Check it. That's 2 squared is 4 and a squared is a squared. The second object will be a 5b being squared. 5 squared is 25, b squared is, well, b squared. So now just following the formula, it's just the first object minus the last object. Notice that I'm keeping the signs the same. And then the first object plus the last object. Often you will run into advanced cases where you have something like, let's say 16x squared y squared minus 1. It's not super advanced, but it's advanced enough. If you see that, you again hope that it's a difference of squares. A 1 is actually a 1 squared. This is a 4xy. So again, first minus last, 4xy minus the last term, which is 1. And then first plus last. You always ask yourself at the end, can you factor any further? In this you cannot, because these are not differences of squares in here. This is not a difference of squares, and there's no such thing as a sum of squares. You cannot break apart a sum of squares. Now I said only 2, but actually I just thought of 2 more, so I'm going to do these last 2. X to the 4th minus 81. This is an interesting problem because this is a difference of squares, actually. 81 is just 9 squared, and x to the 4th is x squared being squared. So if you write that as a difference of squares, it's x squared, the first object, minus the last object, times the first object plus the last object. And again, you rinse and repeat. In other words, you check through this to see if any of these binomials, either of these binomials, factor. And I see that the first binomial is again a difference of squares. It's an x minus 3 times an x plus 3. But the second binomial, it's just a sum of squares. There's no formula for it, so it's just prime. It's locked. And finally, as a nice, interesting, fun example, let's suppose you have something like a quantity x plus 2 squared minus y squared. Well, again, you do have a first item, that's this whole thing, and you have a last item, which is y. So it will factor into the product of 2 binomials, where the first binomial is the first object minus that last object. And the second binomial is the first object plus the last object. That's the factorization. Okay, I think that's pretty much it. Like I said, I'll do a video on a proof of that factorization method, so that instructors who want to see it can see it. You can point your instructors that direction. It's a pretty unique factorization method. So if you use it in a classroom, your instructors might tell you can't because they've never seen it before. So just direct them to the part D of this video series.